Has this ever happened to you? You're walking around on a hot summer day, and the door just won't open. And not even help from your strongest friends will help the door come open. I wonder if our friends from Conair can help. Oh, what good news! It seems as though the Super Cool Group has developed a solution that will save our poor friend. Hi, we're the Super Cool Group, and over the course of the semester, we worked with Conair to develop a solution that eliminates aluminum door frame expansion due to the bimetal effect. The bimetal effect seen in Conair's doors mimics the behavior of composite materials when they thermally expand. Composite materials might have two different coefficients of thermal expansion, which will cause one material to expand more than the other, which will lead to bowing. In the context of a door frame, you see a temperature gradient across the outside surface and inside surface. The outside, hotter surface is exposed to thermal radiation and will therefore expand more than the inside surface, which is exposed to forced cooling. As a consequence, Conair doors might jam during hot summer months where that temperature gradient can get up to 100 degrees Fahrenheit. Thus, for our proposed solution, we wanted to mitigate or eliminate the bimetal effect in Conair's doors. There are three main things that went into performing this project. Our goal was to either reduce the temperature difference between the surfaces to match their deformation rates, to provide structural support to the inside of the frame so that even if there is a high temperature difference, we're not seeing the same level of deformation or jamming. And our main goal was to use COMSOL, an advanced multi-physics package, to create an application that models heat transfer in Conair 500T series door frames, and then use that as our model. Specific specifications that went into designing this product include mitigating or eliminating deflection and expansion from the bimetal effect and requisite thermal and mechanical strains. We wanted to maintain the exterior profile and coloration for their commercial door applications so that companies that already trust Conair are able to continue to use their products with superior performance. Additionally, we wanted to ensure that this does not negatively affect the thermal efficiency of the aluminum urethane thermal break. And we needed to ensure that we had minimal material and manufacturing costs for this door frame. The efficacy of our models in actually eliminating this effect are based on the results of an experiment performed by Conair where they used heat lamps to emulate the effects you might see in the summer in places like Arizona or New Mexico. Only the bottom rail of the door was used in this experiment. We find an experimental linear expansion of 0.06 inches and an experimental linear deflection of 0.038 inches.
Here we have all the material properties that we used in our simulation. These properties were obtained from industry standards, NFRC documents, and research papers. Here we have a thermal circuit for the door frame. This circuit was used to determine the temperature at each aluminum urethane interface and see how much of the heat was dissipated by the aluminum. From our calculations, we determined that the aluminum effectively dispersed none of the thermal energy, and almost all of it was done by the urethane thermal break, as seen by the calculated T1 and T2 values.
In order to create a good finite element model, you need to set boundary conditions that show the system what heat transfer sources should be occurring in the problem. This shows all of the different thermal constraints that we placed on our load when creating our base condition model, which we added to when we created solutions to mitigate this effect. We also set boundary conditions on loading that ensure that the only deformation that we're tracking is deformation from sources that are relevant to this problem. We also set separate boundary conditions with similar constraints to emulate deflection independently of expansion.
First, a simulation has been run on the base unmodified door frame, and the resulting linear expansion and deflection values closely match those of the physical experiment run by Conair. The simulated boundary conditions are therefore well validated and are used to verify our design concepts.
This is where we started our project, with brainstorming. We have two main classifications of concept type. There are concepts which attempt to structurally prevent expansion and deflection, such as the bracing, thick and outermost extrusion, and additional extrusion with bracing. Then there are solutions which attempt to manipulate how heat transfer occurs through the extrusions, such as the cap on the outside of the door and fins to dissipate heat. Ultimately, some of our brainstormed concepts were not viable as they would too greatly change the aesthetic layout of the door. namely the concept which proposes machining holes on the inside extrusion for convective cooling.
This is the drawing for the cap design to show the dimensions. The idea behind the cap is to increase the amount of heat the frame undergoes by adding another layer to decrease the overall effect of the bimetallic effect. The outermost extrusion can be made from a light metal, for our experiment aluminum 6063 T5. Then the piece in contact with the frame and cap is made of ABS to decrease the amount of heat transferred to the door frame since it has a low thermal conductivity.
So here we have the simulation results from the cap. As you can see here, the cap was very effective at reducing the overall deflection of the door with a minor change to the amount of linear expansion.
Fin arrays are a common solution to mitigate heat transfer in systems that are heat sensitive, such as on CPUs. In this case, we were constrained to putting the fins on the inside of the door for aesthetic purposes. While they add structural rigidity, the XX material leads to an increase in expansion. We pushed this concept of structural rigidity further by completing interior bracing that heads all the way from the outside of the extrusion to the center extrusion. What we found though was that this gave excess paths for heat transfer and didn't do much to mitigate our problem. Again, with the constraint of ensuring that the outside surface of the door is the correct color for the customer, we wanted to apply a low E coating to a part of the door to reduce the amount of radiation we were seeing. As such, this coating was placed on the inside extrusions as marked in the diagram on the left. We found that this didn't have a significant impact on the results of the simulation.
For this concept, we tried to thicken the two outermost walls of the extrusion to provide structural support to the door frame for a minimal cost. Overall, it had about a 20% reduction in both deflection and expansion. We increased the thickness a second time to a larger value to show that increasing the thickness helped with the deflection, but the added mass also increased the linear expansion of the door frame. So an optimal thickness must be found for this solution to be ideal.
For this solution, reliefs were introduced every 6 inches in the urethane thermal break. With this, there were some improvements to deflection as the material was allowed to expand without additional stress concentrations. However, it didn't ultimately change the outcome of the situation.
From all the concepts we've shown, the most promising concepts we have are the cap, the additional extra thickness, and the fins on the inside of the door due to their effectiveness in reducing deflection and their overall minimal cost or ability to be retrofittable. From these choices, we then modified and combined some of these concepts in order to find out if they would be more effective in any way.
We wanted to try a solution that it combines the thermal efficacy of the cap solution with the structural efficacy of the fin solution. What was found, though, was that the introduction of the fins did not do much to change the deflection values, which were driven by the temperature gradient.
For this concept, we combined both the cap and the thickened walls as a way of having the most effective solution alongside the cheap effective solution to see how they worked in tandem. However, the results were dominated largely by the effectiveness of the cap, making this solution just a more expensive version of the cap. We also simulated the cap with a larger thickness value to see if it made any changes, and the results were still dominated by the cap by itself.
Due to the convenience of combining these solutions, we tried testing 6-inch urethane breaks with thickened walls. What we found, though, was that the thickened walls had a much greater effect on the solution, and that the values we were seeing from the results of our simulation were almost identical to those of the thickened walls alone.
For this concept, we tried removing the ABS plate in the middle of the cap to see if it was necessary as a thermal insulator, and we found that the results were almost identical to the cap with the ABS plate. From our modified concepts, we found that all solutions were strictly dominated by the cap's effectiveness, but the cap with the ABS clips could be seen as a cheaper alternative to just the cap by itself. From all our solutions, we chose the cap with the ABS clips due to none of the combined solutions being more effective than the cap by itself, and the cap with the ABS clips just being a cheaper alternative to the cap. It is worth noting that if cost is the most important factor, the thickened wall solutions might be more cost efficient, but less efficient at reducing deflection.
To validate our simulations, experimentation should be used to verify these results in our solutions. As you can see here, schematics showing a certain type of experimentation can be done to verify our results. The IR cameras can be used to visualize temperature spreads while the sample is heated and cooled on either side. Thermocouples will record the surface temperatures, and the strain gauges will determine the displacement at certain positions of the door frame. The model can also be improved, and this can be done by including the rest of the door frame so that we can have both expansion and deflection in one simulation instead of two, and so that we get a more realistic look at how the door frame interacts and expands under temperature. The fluid domains inside the gap in the door frame can also be modeled to improve our current convection parameters and have a more accurate model.
In conclusion, all of our concepts focus largely on reducing the temperature gradient across the door frame or adding structural support as the most effective ways to reduce deflection. The expansion was caused mostly by the aluminum's coefficient of thermal expansion and was largely unchangeable unless a different material will be chosen for the door frame. The cap with the ABS clips was chosen as our solution due to its deflection reduction amount and the decreased cost compared to the normal cap. Any future testing could be able to run experiments with these concepts to confirm our simulation results, and we can improve the simulation model by changing our convection parameters and adding fluid domains.